All right, recording resumed, and let's start this Kahoot. Here we go. We're in the middle of dynamics and forces questions, Newton's laws. Some questions related to Newton's laws coming up right here. Pressure. Pressure is defined as there you go. Force per unit area. Hey guys, is that Newtons per square meter, right? Newtons per square meter, which itself has a name. What was that called? What is 1 Newton per square meter called? 1 Pascal, right? You can quantify pressure in pascals. Hey, do you guys know some other ways to quantify pressure? Atmosphere, yeah. How many atmospheres? Like we're sitting in 1 atmosphere of pressure right now, right? Sea level. How about PSI, right? Pounds per square inch. Right? Go buy an American bike pump. Oh, see that? All right, points on the board. There we go. If force acting on a cart doubles, what happens to the cart's acceleration? Yeah, would also double, right? So double the force, double the acceleration. That brings us over here. That is a Newton's second law of motion question. Yeah, so we're kind of in the vicinity of Newton's second law of motion here. All these questions are kind of in order, right? So why does something accelerate? Well, because there's a force on it. How much does it accelerate? Well, force acting on mass. There you go, net force on mass. So if you double the force, you'll double the acceleration. While I got the screen flip, let's look at all Newton's laws of motion. Right? So yesterday, near the end of class, you guys saw some law of inertia questions, right? Right. Objects want to travel in a straight line at constant velocity if they can, right? Things ever speeding up, slow down, and going around a curve, there's an external force. Here's Newton's second law of motion. Acceleration is caused by net force acting on the mass. Right? And then a few minutes from now, you guys are going to get some third law questions. This is the equal and opposite rule. Whenever two objects are interacting, like pushing or pulling on each other, forces are always equal and opposite. Right? Is the third law, right? So won't see those right away, but pretty soon those are coming up. All right, you guys good so far? Good so far? All right, we got Sydney, Stephen, E, Alec, and Addie. Suppose cart is being pushed by force. Suddenly, a load is dumped into the cart so that the cart's mass doubles. What happens to the acceleration? Yeah, get half. Right. So, all right, you guys knock that one out real fast. Look at the poster. Right. Sorry, pushing a cart with some force. If you double the mass, you get half the acceleration. Boom. Okay. Inverse relationship. Huh? You guys all right? You guys set? Oh, well, sorry. Gotta move on. Nothing there. I got Melissa, Steven, Alec, E, Addie. 20 Newton falling object encounters 4 Newtons air resistance. What is the net force? It should be 16 Newtons. Okay, I got some follow-up questions about that. Ooh, I was gonna steal off my notes from last class, but don't see this one right away. So let's reconstruct this one real fast. Got a ball, weighs, ruler, 20 Newtons. That's, maybe I should say mg equals, right, the weight. Right? And now, guys, in a vacuum, that would be the end of the story, right? But if you're talking about air drag, F drag is 4 Newtons, right? Okay, so now we're getting the sum of forces, the net force is 20 minus 4. 20 minus 4 is 16 Newtons, 16 Newton net force. Okay. I got a couple other questions. Guess what is the mass of that ball? 2 kilogram. Yeah, 2 kilogram. Because weight is mg. Earth's gravity field is 10 meters per second squared. 2 times 10 would be 20 Newton. Right? 2 kilograms weighs 20 Newtons. Right? So I just dropped something off a cliff that's like twice as massive, twice as heavy as this guy right here. Right? All right. So for this snapshot right here, guys, what is the acceleration of this ball right here? How much? 16 Newton net force acting on 2 kilograms mass. So like 8 meter per second squared, right? 8 meters per second squared. Oh, look at that. Right, there's a little bit of air drag, so it's not accelerating at the full rate of gravity. Right? Ba-boom. Points. 6 Newton falling object encounters 6 newtons of air resistance. What is the net force? 0 newtons. Hey guys, is that equilibrium? Equilibrium? It's falling. Is it still equilibrium? Yeah. So 0 net force. It's going down at constant velocity. Is that called terminal velocity? Well, it's reached terminal velocity, however fast it's going, which might be different for different shapes. If it has a little parachute attached to it, it might be not going as fast. All right. High school student hits a nail with a hammer. During this collision, there is a force. Yeah, on both the nail and the hammer, both the hammer and the nail. Right. You guys, which force is bigger, the force on the nail or the force back on the hammer? Equal. Equal magnitude forces. Right. Ooh, so I guess we're in Newton's third law now. I guess we've hit Newton's third law questions. I got E, Alec, Melissa, Stephen, Addie. As a ball falls, the action force is Earth's mass pulling on the ball. What is the reaction force? Yeah, Earth pulls so Earth pulls down on the ball. The ball pulls up on the entire Earth. Right? That's the action and reaction pair. Right? Guys, which of those forces is bigger? The Earth pulling down on the ball or the ball pulling up on the Earth?
Earth pulling down on the ball.
Same force. Newton's third law, equal and opposite. When you have two objects, in this case, pulling on each other, same force. Right? But hold on, why is the ball accelerating? But the Earth is basically not moving. Earth has so much mass. So much mass, so much inertia. So equal forces, right? Different masses, different accelerations. If you pick the red one, some of you guys did. That's a different action reaction pair going on. So the the ball pushing against the air and the air pushing back against the ball. That's a different action reaction going on. Okay? Yeah, so Earth pulls the ball pulls up on the Earth. There you go. Steve, Reese, Alex, Steven, Addie. Unfortunate bug splatters against the windshield of a moving car. Compared to the force of car on bug, the force of the bug on the car. There you go. Same force. Right? Car on bug on car, same force, same magnitude force. Right? Unfortunate bug splatters against windshield of a moving car compared to the acceleration of the car, the acceleration of the bug. It's change in motion. Yeah, much larger, right? If you always think about now, it started out as Newton's third law. That was the previous question, but now we can kind of kick back to Newton's second law of motion. Think, well, what's the consequence for acceleration, right? Think about this in terms of kinematic first, and I'll flip the screen over. So kinematic motion, like the rate change in motion. So from the car's point of view, you're sitting in the car, you're driving along I-95, and then bang over against a bug, right? Does that slow the car down? Maybe a tiny bit, but it'd be like negligible. You wouldn't notice, right? Maybe you notice if it was like a billion bugs, but if it's like one bug, you hardly anything. But from the bug's point of view, right, that's a huge change in motion, right? It's a huge change in motion, right? So that's a kinematic way of thinking of it. I'll switch over here. Right, here's Newton's second law of motion way of thinking about it. Right, it's the same force on the cars on the bug, but different masses. Divided by 1,000 kilogram car, that's close to zero acceleration per car. Or I think the phrasing on your paper says deceleration, but same idea, right? Negative acceleration. And then deceleration is kind of a colloquial term, right? And then if you divide that same force by like a 1 gram bug, that's a huge change in motion. with that bug during that collision. All right, next. Let's see how we're doing on points here. We got Reese, Max, Alex, Steven, Addy. Whenever an object exerts a force on another object, the second object exerts a force the same magnitude in the opposite direction that of that on the first object. True. Yeah, so that's just Newton's third law stated in sentence form. There you go, Newton's third law. All right, Max moving up. Steven, Addy in the lead. A person is attracted toward the center of the Earth with 430 Newton's gravitational force. The person pulls up on Earth with yeah, 430 Newtons. Right. When you're standing on a scale, yeah, that's your weight pull down towards Earth. That's also Earth pulling up, pushed into you. Same force. All right. Ooh. Large truck, small car, head-on collision. The vehicle to undergo a greater change in velocity. A small car, right? Right. So it's the same force on both vehicles. Right? Hey, this reminds me a lot of the bug versus the car, right? Right. So same forces, but different masses, different accelerations. Yeah. Yeah. So yeah, small car. Take that force divided by a small mass. It's going to accelerate a lot. It's going to change state of motion a lot. Right? If you happen to be in that collision, would you be safer inside the small car or safer inside the large truck? Large truck, yeah, you're safer in large truck, right? Because that large truck doesn't change its motion as much. Okay. I got Melissa, Steven, Alec, Max, Addy. For 10,000. Two people pull rope, tug of war. Each person pulls with 400 Newtons force. What is the tension in the rope? Uh, 400 Newtons. This question always trips everyone up, but there you go. All right, 400 Newtons. Let's look at here. I just got my notes from last class. Just save us a little time here. Okay. Try to get this all in class period. So, two guys pulling rope tug of war. This guy's pulling with 400 Newtons force. This was AP. I better have my force vector connected to like some dot. I guess I'm looking at one point on the rope, trying to analyze it, right? 400 Newtons pull left. Well, if that point is in equilibrium, then there must be zero net force. So there has to be 400 Newtons tension to the right. Ah, there you go. There's your tension force there. Okay? If you cut the rope and you put in one of these spring scales in the middle, right, that's what I got right here. That spring scale is going to read 400 Newtons. Ooh, okay. This guy over here on the right is also pulling with 400 Newtons. So it's 400 Newtons everywhere. If you replace this guy on the right with the tree, then these two situations are physically equivalent. Same thing, right? The tree is pulling now with 400 Newtons of force, right? But the tension's still at 400 Newtons. Yeah, 400 Newtons everywhere. Oh, Steven, moving up to the top. Newton had the original insight to see that. What did Newton see that no one else before him saw? Yeah. So Newton is the first guy to recognize that an apple pulling down to Earth or the moon orbiting Earth is the same phenomenon. There's a gravitational force involved with both of those. Right? The blue and the yellow, people have known for a long time, but Newton unified. Before Newton, people thought that there were two different laws of physics. There must be terrestrial laws and celestial laws, and Newton says, no, actually, it's all one set of laws. Yeah, Steve, Alec, Addy, Max, Steven. Newton reasoned that gravitational attraction between Earth and the moon must be okay. So reduced by distance is talking about inverse relationship. Okay, so what does the phrasing mean? Right. Independent of distance means that it's the same force regardless of your location, which isn't quite true. Like the further away you get from a planet, the less gravity pull from the planet. Directly proportional means like a linear relationship. So what that one literally means is when you increase the distance, the gravity force also increases. That's opposite. That's opposite, right? Reduced by distance, what I'm looking for. In fact, it's not just reduced by distance, which is inverse. More specifically, it's an inverse square relationship. Right. So we're moving on to this right here, universal gravitation we got going on. Universal gravitation. Okay. So force between say two objects, right? The force is proportional to 1 over the distance squared. There you go, right? So as you get further away, less gravitational pull. Yeah. Forces reduced with distance. All right. That's what I was trying to get at. All right. Bet you guys could write the equation there, right? If the radius of Earth decreased with no change in mass, so we're just squashing the Earth down, what would your weight be at the surface? Yeah. All right. All right. Yeah, you would get heavier. Okay. Here, I was gonna flip my screen over anyway. Okay, so let's look at this. Okay. So one specific version of this is if you are at the surface of the planet, in which case this variable general R becomes maybe make that a capital R for like a fixed radial size of the planet, right? And then this force would represent your weight, right? Right. Now let's take that question. So we're gonna crunch down the Earth. Right? So what changes would stay the same? Universal gravity constant, that's the same. The mass of the Earth, we're also going to leave the same. We're just like smashing it, right? Your mass is the same. All these numerators stuff is the same, right? But the radial size would be decreasing, getting smaller, smaller, smaller. Hey, guess what happens in a fraction when you divide by smaller values? The overall fraction gets bigger. Yeah. So if you're standing on a scale, it's almost like crunching down the Earth. Yeah, you would actually weigh more and more. Ooh. Oh, we got Reese, Alex, Steve, Max, Steven. Gravitational force between two spheres, 100 newtons. If the distance between those is doubled, what's the new force? So should it be a quarter of its value? If you double the distance, 1 over 2 squared. Here, I know I actually had an update to that version of this poster. You guys know I noticed I put in a universal gravity constant. So here, we're looking at what's the relationship between these two right here. Guys, if you double this distance, factor 2 squared, isn't that 1 over 4, like 1/4? So if your original weight was 100 newtons, a quarter of that is only 25 newtons. Ooh, quarter, right? 1 over r squared. So yeah, inverse square relationship between force and distance. Steve, Sydney, Alex, Max, Steven. Top 5. By noticing Uranus's orbit is perturbed and using law of gravitation, 2 astronomers independently discovered. Yeah, Neptune. You guys might remember that was a specific Paul Hewitt story. Yeah, there was these astronomers. They were watching the orbit of Uranus. They noticed it didn't move exactly what Kepler and Newton would have said. They said, well, it's like a tiny fraction of a degree off in the sky. So why is it? Is gravity breaking down? What's going on? Somebody said, oh, hold on a minute. If there was a planet of like some mass and some location out there, it would cause that motion. They point their telescopes up in the sky. Oh, there's Neptune. Neptune was discovered on paper with physics before it was ever discovered through a telescope. All right. The force of gravity on you is greatest when you are standing at Earth's surface. Okay, now this was a specific story I walked you guys through a few months ago. So let's walk through the story. I think I did make a poster, so I just want to have it printed out. Right? But like, what is the gravitational force on you? Your weight as a function of your location from the center of Earth. Right? So I have a lowercase r. This is some generic, just like a variable distance, right? And I have capital R is like the fixed radius of the planet. Now all of us spend our entire lives at this fixed capital R radius of the planet, right? From the center of Earth. Right? From the point of view of these equations, the distance between you and the Earth is the radius of the Earth, right? Right. So that could be capital R. Right? So if I make a graph, right, gravitational force on you versus your distance, right? all of us are all familiar with this point right here because we lived our entire lives here. Right? At the surface of Earth, we have some weight. Okay. Now, what if you take a shovel, it's got a little shovel, you dig a spiral tunnel all the way down center. Let's ignore all the molten magma. And let's say there's like a cave at the center. Guess what is your weight right at the center? 0, because every grain of sand on Earth pulls you a different way. Gravity cancels out. Okay, so that point has to exist. Right? Now, I think you guys should be able to, somewhere in your textbook questions or solutions a few months ago, I'm pretty sure I derived for you guys why this would be a linear relationship. Now, it's assuming a planet of uniform density. In AP, it's good to be able to do that, or take some paper and some time. Right? Now, what if you take off in a rocket and fly away from there? Right? As you get further and further away, the gravity force would taper off 1 over the distance squared. Right? And graphically, that looks kind of like this. Look, it's asymptotically approaching 0. So like by the time this rocket gets to Mars, is there a gravity pull from Earth? You get tiny, 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 right? Like almost 0 at that point. Right? Okay, so see you guys. Yeah, so the most you'll ever weigh in the vicinity of any planet is right at the surface. Yeah. All right, guys get that? Yeah. All right. Ooh, got Steve, Alec, Addie moving up on fire. Max and Steven in the lead. Reason the moon does not fall into Earth is yeah, sufficiently large orbital speed. All right, you guys got that one. Sufficiently large orbital speed. All right, why does anything stay in orbit? Well, because it's move into the side fast enough, pretty much. Okay. Oh, you guys remember this one right here? You can calculate orbital speed. Guys, this is a real short proof. Boom, boom, boom. So, see, if anything's like on a curved path, some centripetal force you need, right? In this case, provided by only one force, gravitational force, right? And then, you guys derived this in your lab with the Play-Doh canisters and the pipe and the string, right? Centripetal force, right? Here's Newton's universal law of gravitation. Let's say the moon orbiting the Earth, for example, the moon orbiting the Earth, right? Notice the mass of the moon, cancels out, right? So how fast does the moon have to go? Well, here's universal gravity constant. Here's the mass of Earth, because that's what's being orbited. And here's the distance from the Earth to the moon, like center to center, right? You should be able to derive this. This would be a completely fair FRQ question. If you could ask you that as an FRQ, right? Like 3 steps. You guys could do that, right? So know that one right there. Be able to derive that orbital speed. There you go. All right, lots of points. 21. Rock and pebble will fall with the same acceleration because the gravitational force on each is. Ooh, all right. Okay, so gravitational force, also called weight. I wonder who the one winner is. I might find out soon. That's called weight. Guys, a big old rock and a little tiny pebble, those have different weights, right? Different weights, right? But if you drop them from a cliff top, hey, don't they accelerate the same and hit the ground at the same time? Right, so here, I'm gonna flip my screen over. This is actually Newton's second law of motion question. Let's go back to Newton's second law. Here, it's this one right here. Okay, so a bunch of objects at the surface of a planet, they all have lots of different weights, lots of different masses, but the ratio, so you drop any object at the surface of Earth, this ratio is gravity field, and for Earth, that number is about 9.8 meters per second squared. Right? A lot of times we say about 10 meters per second squared gravity field. There we go. Different weights, different masses, but the same ratio of force to mass. Right? Who got them points? Steven! Standing in the lead. Value of acceleration due to gravity. All right, all the above. Right. Depends on the mass of the planet, gravity field of the planet. Sorry. Mass of the planet, radial size of the planet. It's different on different planets. For Earth, pretty close to 10 meters per second squared. Like Mars is like 3.7 meter per second squared. Right. Oftentimes, AP will swap out the unit for gravity field instead of saying meter per second squared. Do you guys know the alternate unit for gravity field? if it's not meter per second squared. Here. What's force measured in? Newton. What's mass measured in? Kilogram. Ah, could gravity field be some Newton per kilogram? Right. Right. A lot of times you'll see AP do that. They'll swap out the units for gravity field. Newton per kilogram. All right. Steven got 7 in a row. Gravity field strength at the center of Earth is zero gravity field at the center. Every point on Earth pulls you a different direction. Gravity field cancels out. All right. If you were to weigh yourself in an elevator in free fall compared to your ordinary weight, somebody cut the cable. Ah, what do you weigh? What's your apparent weight? All right, that's what I'm looking for. Apparent weight. I guess you could kind of make a case the Earth is actually pulling out with the same gravity force. But yeah, your apparent weight, like if you brought a scale, right? Yeah, you feel just like an astronaut, right? If you brought a scale and you try to stay on the scale, well, everything's floating around. Scale's reading 0 newtons. Okay? Interesting side thought here. I think Einstein called this the best thought he ever had, or some version of that, because he made this connection. He realized that from the observer's point of view, it would be impossible to tell the difference between this scenario and actually being in the middle of space, right? Did some work with relativity with that. Interesting, right? So that's a whole different story there. All right, Steve, Alec, Max, Addy, Steven. At the top of a ladder as tall as Earth's radius, your weight would be oh, where'd you guys go? Yeah, a quarter of your surface weight. I got a picture for you guys. Picture time. All right, so you're walking around on the surface. You have something. Let's say you weigh like 100 pounds, right? 100 pounds. And you come across this, like, hey, look, it's a giant Jack and the Beanstalk ladder. So you walk up to the top of that, bring your bathroom scale with you, of course. And now you stand there. Hey, okay, you guys see you've effectively doubled your distance from the center of the Earth, right? So inverse square law, 1 over factor of 2 squared. Yeah, you weigh only a quarter of your weight up here. So 100 pounds on the surface is like 25 pounds at the top of the ladder. Yeah, 1/4. GMM on R squared. 1 over the distance squared. There you go. Lots of points. Why did Newton think there was a force acting on the moon? Oh yeah, because the moon follows a curved path, right? Yeah, so guys, does something need a force on it to be in motion, just to be moving? No. All right, so yesterday, I think a few times I mentioned Voyager spacecraft, right? It's been moving for decades, but it doesn't need a force. It's just moving because of inertia, right? It's just going, right? But you know what else? So that's like Newton's first law of motion, law of inertia. But something else law of inertia says is that if something is in motion, it only wants to follow what kind of path? Straight line path, straight line path. Okay? Newton knows that. He looks at the moon and says, hold on, that moon is like on a curved path. Therefore, there must be a force on it. Oh, okay. All right. We made a tie-in with gravity, right? Gravitational force acting as its centripetal force. Right? It's on a curved path. If you drop a stone drilled into a hole drilled all the way to the other side of the Earth, the stone will. Right, so yeah, the correct answer of the ones provided is speed up until it gets to the center, right? Is what I'm looking for, right? So let's look at this picture right here. Right? So you walk along, then you see, oh, there's a big old hole. Oh, whoa, I can see all the way to Australia. Right, so then you drop the stone, right? So it's gonna speed up as it gets to the center, faster, faster, faster. Right? Now the gravity pull on it actually decreases which we don't normally run into in this class. That's a rare thing you run into, right? But yeah, you guys know at the middle there's no gravity field, but don't forget it's moving really fast. It's still got a bunch of momentum, so it's gonna overshoot the equilibrium position. It's gonna keep going, keep going, keep going, but slow it down, slow it down, slow it down, slow it down, because now the net force is the other way, but it's smooth, right? And it'll keep going all the way until it just peaks through on the other side. Right here's this Australian guy, and then it'll fall back through. Now, if there's no frictional loss, like no drag force, then it'll just oscillate back and forth. So it's speeding up to the center, and then once it crosses the center, it slows down, right? And it just oscillates back and forth just like that. It's kind of analogous to when I see you guys back in January after the break. We're gonna do the last section we haven't done yet, which is oscillation. Okay? What if you take a mass, put it on a spring, pull it, let it go, that would oscillate back and forth. Okay? There's some equilibrium position. It's gonna like keep flying through, like overshooting. And if you made a position versus time graph for that, I bet it looked like something like a sine or a cosine graph, like oscillating, something like that. Or if you made a velocity versus time or acceleration versus time, that some really similar type looking graphs. All right. Speed of a satellite in circular orbit. Yeah, constant. There you go. Right, that's the orbital speed of square root gm on r. Right. Now, remember Kepler way back in the day was looking at planets saying, actually planets don't follow exactly circular paths. It's kind of a tenuous dynamic equilibrium type, right? Because if it went any slower, it would just eventually spiral into the sun, right? Ellipses are a bit more stable, yeah, elliptical paths, right? So planetary paths are slightly elliptical. The speed of a satellite in elliptical orbit. Is variable. There you go. Like speed up and slowing down. Right. Everybody get that. Let's look at a picture real fast. You guys remember a few weeks back, I gave you guys some string. You made a loop of string, put down a couple of pins, and took a third pin with the string, and then went all the way around. Right. That made an ellipse. Right. Now planetary orbits are slightly elliptical. Maybe this could be a comet. Here could be the sun. Right. Maybe you put down a couple of pins and take a string, goes like that. Right. Highly elliptical. Right. So here's a comet. Come from maybe the Kuiper belt over here, like it's knocking. So here it's going slow and then faster, 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 and then zoom, really fast around the sun, and then like slows down. So slow on this side, fast on this side. Right? There's some good conservation of energy questions related to that, like potential kinetic energy. I think that question might be coming up tomorrow. Yeah. All right, we got Steve, Alec, Max, Ade, Steven. A black hole is an object that all right. Yeah, we haven't talked about this so much. Maybe briefly next semester. Right. So if you have a star at least 3 times the mass of our sun, end of its life cycle, it'll collapse, form a crazy dense ball, where the necessary escape speed would. Oh, since I mentioned escape speed, let me erase over here real fast. Right. The necessary escape speed would be greater than the speed of light, so not even light can escape. Right. So here's a bunch of stuff all shoved in one poster. Gravity field for this guy, 9.8 meters per second squared, comes from this. Right. Orbital speed for the satellite, boom, like that. Right. AP will never ask about escape speed. You can derive this from conservation of energy, but I've never seen them ask that. Right. And then, yeah, has crazy density, right? Also, if you're in the vicinity of a black hole, get a theory of relativity, time actually slows down. So yeah, a lot of crazy stuff. Black holes, they are fun unless you're there. When a star collapses to form a black hole, its mass stays the same, right? So that's just conservation of mass, right? Conservation of mass, right? No, maybe its density changes, right? Like I've read if you squeeze the entire Earth down to like the size of a coin, right? That's the density you're talking about. That's like the density of a black hole, right? Yeah, it's conservation of mass. This gets really dense. Right? If the sun were to collapse into a black hole, it won't happen, but if it did, what would Earth do? So we're looking for orbit the black hole just as it orbits the sun now. Okay. We try to back that up with some equations over here. Okay. Oh, well, here's the orbital speed we're looking at, right? So, and then where's my other one? Right? Maybe here's the picture, right? So what if instead of the Earth and the Moon, what if this was the sun and this was the Earth? Is that okay? Right? And the sun like collapses into the black hole. Well, what changes here? Universal gravity constant, that's the same. The mass of the sun now black hole, that's the same. Mass of the Earth, that's the same. This distance is the same. How about this poster? The Earth like had some orbital speed, right? So it's gonna keep doing so. Yeah. So from this point of view, like nothing really changes about the orbital mechanics. Yeah. So the Earth just keep going right around. Yeah, true. Dark and cold. Keep going. I got Alec, Reese, Max, Addie, Steven. Early bird communication satellite hovers over the same point on Earth's equator indefinitely because yeah, orbital period 24 hours. So think about yeah, orbital period 24 hours is what I'm looking at. Okay. So this orbital speed, notice that the mass of the satellite cancels out, right? And then however fast you have to go depends on, well, universal gravity constant, the mass of the planet that's being orbited, and also this distance to this is the distance to the center of the planet, right? So like low Earth orbit, this is just a little bit bigger than the radius of the planet, like proportionally, right? And if you figure out how much time does it take to go around, then it ends up being about, do you guys know? Right, International Space Station in low Earth orbit, how much time did it take to go around? About 90 minutes, right? You did, right? But if you just back up to like the orbital path of the moon, the moon takes about 4 weeks to go around. Right? Somewhere between those two, between low Earth orbit and the moon, is there's a place where you can set up a geosynchronous orbit, right? So geosynchronous, it can match the rotation of the Earth. Okay? And then from the point of view of satellite, it's only hovering above one point on Earth. And if you're down on the equator looking up at it, it's like, hey, it's hovering up in the sky, right? All day, every day. Got E, Alec, Max, Addie, Steven. Compared to period of a satellite in orbit close to Earth, the period of a satellite in orbit far from Earth. Yeah, would be longer. So think about low Earth orbit versus geosynchronous versus the moon, right? The further out it's going, not only the further path has to go, like bigger circumference, but it's also going slower. So definitely, yeah, takes more time. Okay? There's a connection there to Kepler's third law of planetary motion. It's like a time squared, distance cubed, proportional relationship, something like that. I got Reese, E, Mac, Ade, Steven. In physics, work is defined. Okay, so work and energy. Work is defined as force times distance. So work is a transfer of energy. If you push on something with some force for some distance, okay, now that's a dot product. So you only multiply together the parallel components. This is force dot distance, right? Parallel components, right? And guys, that has units of what? Joules. Yeah. So newtons times meters makes joules, right? Now, you learned this a few weeks ago. More recently, you guys learned something called torque, right? Which was R cross F, which was in units of Newton meters, which looks a lot like this, except let's see, it's a cross product, not a dot product, right? Now remember, that's a completely different concept though, right? So R cross F for torque in Newton meters has nothing really to do with work, force dot distance, which is in joules, right? Totally different concepts, right? Energy is something that's conserved. You can transfer it. Right? Torque is like a rotational moment. Right? There's a question coming up pretty soon that links these guys, right? So here, we'll set up this question that's coming up pretty soon, right? What if I lift something some height, right? Do I have to apply a force equal to about its own weight to lift it at constant speed? Right? and the distance I lift it could be the height that I give it. Ooh, so if I set this on a shelf, the work I did lifting it, isn't that equal to the potential energy that I give it? Gravitational potential energy. I forget if that's the next question, but it's one of these coming up pretty soon. Lots of points. Nellie Newton pushes twice the force for twice the distance. She does, what is double, double? Double the force, double the distance. Double, double is 4 times. There you go. So for example, you lift some weight up a meter, it took some energy to do that. Right? If you lift twice the weight, twice the height, take 4 times the energy it takes to do that. Power defined as work per unit time. So you could call that a rate of work, a rate of energy transfer. Right? That's what power is. Oh, guys, what's the unit for power? Watts. So there you go. So joules per second is watts. If you look on a light bulb, it says 40 watts. It's drawing 40 joules per second. That's what it is, right? Now let's look at this one where we're at it. I could totally see AP asking this, right? AP questions like this before, right? There's a different perspective on power. So work is force dot distance. This is that substitution. Hey, what if I rope these two variables together? Guys, distance over time. What is that called? Velocity, right? Velocity. Okay, so elevator physics. Got an elevator. Let's say it's being pulled up at constant velocity. There's some motor at the top of the elevator shaft, some number of watts. Hey, I wonder how many watts it's drawn. What's the power output of this motor at the top of the shaft? Right. Well, if you know, say the tension in this cable, right, which would match the weight at constant velocity, and you know the speed it's being pulled up at, just boom, boom, put that together. Right, force and velocity. Right. Guys, memorize that one because that might pick you up a couple of points on the AP exam, just having memorized that. That could be a multiple choice question. That would actually make a pretty good FRQ too. Right? Have you derive that short derivation, right? Amount of potential energy possessed by an elevated object is equal to. Yeah, the work done lifting it. All right, that's the one I was pointing out on the poster, right? Work done, right? So weight times height, force times distance, right? MGH. MGH is potential energy, gravitational potential energy. Yeah, work done lifting is equal to the potential energy it ends up with. How much further will a car traveling 100 kilometers an hour skid to a stop compared to one going at 50 kilometers an hour? If you double the speed of the car, brake distance. Yeah, 4 times the braking distance. Let's look at the easiest, most straightforward way to solve that question is with conservation of energy. Well, actually with an open system, right? You guys see kinetic energy minus work done by friction, go to a stop, right? Anyway, the solution to this ends up being this. Here's braking distance as a function of initial speed of the car. Notice the mass of the car cancels out. Right? Now, this is not the only way to solve this. You could solve for acceleration and then go back to kinematic motion, and you get the same answer. Ends up being this, right? Now, interestingly, this relationship right here, I pulled out. So if you double the initial speed of the car, it's going to 4 times the braking distance. Triple the initial speed of the car, that's 9 times the braking distance. It's a good one to know, right? I think it's underappreciated how dangerous cars are. Do you guys know how many people die just in the States every year from car crashes? It's like 40,000 every year. That's been consistent for a while. Yeah, so driving cars, dangerous, good to know. If you triple the speed of the car, you need 9 times the braking distance. As the pendulum swings back and forth, yeah, those are all true statements. Lowest point could be called all kinetic. At the end points, it's all potential. And then energy oscillates back and forth between those two types. With the bronze, Max. With the silver, Eddie. And the gold. Steven. Runners up. E and Reese. Oh, that takes us right to the end of class. All right, perfect timing. So good job, guys. Call it a wrap right there.